We navigate our lives with very little comprehension of how the world truly functions. It's rare for us to contemplate the mechanics that produce the sunlight essential for our survival, or to consider the force of gravity that binds us to the earth and saves us from being flung into the void. We give scant thought to the atoms that form our bodies, whose stability is the foundation of our existence. Children, on the other hand, are a different story. Their knowledge is so limited that they continue to pose the deep questions that most of us have set aside. There are very few people who genuinely grapple with the fundamental workings of nature. From where did the cosmos originate, and has it been here forever? Is it possible for time to one day flow backward, causing effects to happen before their causes? While there may be a final, unbreakable barrier to what humans can understand, I have encountered children, and a few adults, who possess an insatiable need for answers. They are driven to ask, what does the inside of a black hole look like? What is the most fundamental particle in existence? Why can we recall the past, but not anticipate the future? If everything started as chaos, how did the universe become so orderly? Ultimately, why is there a universe at all? In our culture, parents and educators frequently meet these inquiries with a shrug or a vague allusion to religious tales, as some are uncomfortable with subjects that highlight the boundaries of human knowledge. The truth is, these very questions have been the engine for progress throughout the history of philosophy and the natural sciences. A growing number of adults are now exploring these topics, discovering that the answers can be mind-bending, stretching from the subatomic realm to the cosmic scale. We are extending the reach of our inquiry to investigate both the infinitesimally small and the immeasurably large. What have we learned about the universe, and what methods have revealed this knowledge? Where did it all originate, and what is its ultimate destiny? If the universe had a start, what took place before that moment? What is the fundamental essence of time, and will it have an end? Recent advancements in physics, many enabled by extraordinary new technologies, are at last equipping us to tackle some of these ancient puzzles. One day, the solutions to these mysteries might seem as obvious as the Earth revolving around the sun, or they could appear as preposterous as the notion of a world resting on a stack of turtles. Only the passage of time, whatever that may be, will reveal the truth. As far back as 340 BCE, the Greek philosopher Aristotle, in his work On the Heavens, offered two powerful arguments that the Earth is a round sphere, not a flat disk. First, Aristotle reasoned that lunar eclipses are caused by the Earth passing between the Sun and the Moon. Since the Earth consistently projects a circular shadow onto the Moon's surface, it must logically be spherical. Were the Earth a flat disk, its shadow would be an elongated ellipse, unless the eclipse always happened when the Sun was perfectly aligned with the disk's central axis. Second, the Greeks were aware from their travels that the North Star, Polaris, sits lower in the sky when viewed from southern lands compared to northern ones. Given that Polaris is situated directly above the North Pole, an observer there would see it straight overhead, whereas someone at the equator would see it on the horizon. By comparing its apparent location in Egypt and Greece, Aristotle even estimated the Earth's circumference to be 400,000 stadia, an ancient Greek unit of distance. While the exact length of a stadion is not known, it was approximately 200 meters, which means Aristotle's calculation was about double the currently accepted figure. The Greeks also had a third, more intuitive argument for a spherical Earth. When a ship approaches from the sea, why do its sails become visible over the horizon before its hull does? Despite this insight, Aristotle incorrectly believed that the Earth was stationary, with the sun, moon, planets, and stars all moving around it in perfect circles. This conviction stemmed from his mystical view that the Earth was the center of everything, and that circular motion was the most flawless form. In the 2nd century, this idea was developed by Ptolemy into a complete cosmological framework. In his model, the Earth was central, encircled by 7 spheres that carried the moon, the sun, and the 5 planets known at the time: Mercury, Venus, Mars, Jupiter, and Saturn. Ptolemy proposed that the planets themselves traveled in smaller circles fixed to their larger spheres, a mechanism that accounted for their complicated trajectories across the sky. The final, outermost sphere held the fixed stars, which appeared to move in unison while keeping their positions relative to one another. The model offered no explanation for what existed beyond this last sphere, as it was considered outside the bounds of the observable universe. Ptolemy's system could forecast the positions of celestial bodies with a reasonable degree of accuracy. However, to achieve this precision, he had to accept an orbit for the moon that brought it twice as close to the Earth at certain points, which would mean its apparent size should double. Ptolemy recognized this inconsistency, yet his model gained widespread acceptance, even if it wasn't universally held. The Christian Church embraced Ptolemy's universe, finding it consistent with Scripture because it left an abundance of space beyond the sphere of fixed stars for both heaven and hell. It wasn't until 1514 that a Polish priest, Nicolaus Copernicus, put forth a far simpler concept. Fearing he would be condemned as a heretic by the Church, Copernicus initially circulated his model without attribution. His revolutionary idea was that the sun was motionless at the center of the cosmos, and that the Earth and the other planets traveled around it in circular orbits. It would take nearly a full century for this theory to be considered seriously. Eventually, 2 astronomers, Johannes Kepler from Germany and Galileo Galilei from Italy, began to publicly champion the Copernican view. Although the orbits Copernicus described didn't align perfectly with observations, his work ultimately led to the downfall of the theories of Aristotle and Ptolemy. In 1609, the entire field was transformed when Galileo pointed a newly invented telescope toward the night sky. When Galileo aimed his telescope at Jupiter, he revealed that several small moons were circling the planet. This observation was revolutionary because it demonstrated that not every celestial object had to orbit the Earth directly, which was a core claim made by Aristotle and Ptolemy. Of course, you could still try to preserve the Earth-centered model by imagining that Jupiter's moons traced incredibly complex paths around our world, only giving the illusion of orbiting Jupiter. Nevertheless, the theory put forth by Copernicus was vastly more straightforward. To make the model even more accurate, Johannes Kepler later refined Copernicus's work by suggesting that the planets travel not in perfect circles, but along ellipses, which are essentially stretched-out circles. With this crucial adjustment, the predictions of the theory finally aligned with what astronomers were actually observing. For Kepler, however, these elliptical orbits felt like a makeshift hypothesis. An ellipse, after all, is far less perfect than a circle. He had stumbled upon the fact that ellipses fit the data, but he could never square this discovery with his own idea that magnetic forces from the sun were pushing the planets around. The explanation for this puzzle wouldn't arrive until much later, in 1687, when Isaac Newton published his work, The Mathematical Principles of Natural Philosophy, **. In this book, Newton did more than just propose a theory of how objects move through space and time. He also developed the complex mathematical tools required to analyze that motion. Furthermore, Newton put forward the law of universal gravitation, which states that every body in the universe attracts every other body with a force determined by their masses and the distance between them. This is precisely the same force that causes an object to fall to the earth. The story that Newton was inspired by an apple literally hitting him on the head is almost certainly untrue. What Newton himself said was that the idea of gravity came to him as he sat in a contemplative state, and the sight of a falling apple sparked the thought. He then went on to show how, according to his law, the moon follows an elliptical orbit around the Earth, and how the Earth and other planets trace their own elliptical paths around the sun, all governed by gravitational forces. Copernicus's model had already dismantled the idea of Ptolemy's celestial spheres, and along with them, the notion that the universe possessed a natural, finite boundary. Given that the distant stars don't seem to move in relation to one another, apart from the nightly rotation caused by our own planet's spin, it seemed logical to conclude they were objects similar to our sun, only located at much greater distances. Newton, however, realized that his theory of gravity implied these stars should be attracting each other, meaning they couldn't possibly remain perfectly still. This led to a significant question. Shouldn't all the stars eventually fall together, collapsing into one central point? In a letter to Richard Bentley in 1691, another prominent thinker of the era, Newton contended that this exact outcome would be inevitable if there were a finite number of stars within a finite region of space. Even in an infinite cosmos, he argued, the stars in any given region would still collapse toward their own center, as the gravitational pull from stars outside that region would, on average, cancel out. We now recognize that an infinite, static model of the universe is simply not viable if gravitational forces are always attractive. It's interesting that before the start of the 20th century, nobody seemed to entertain the idea that the universe might be expanding or contracting. The universal assumption was either that the universe had existed forever in an unchanging state, or that it was created at some point in the past, looking much as you see it today. I think this belief can partly be chalked up to our human tendency to seek out eternal truths, and the comfort that comes from believing that while we are mortal, the universe itself is eternal and constant. Even those scientists who understood that Newton's theory of gravitation made a static universe impossible did not then consider a dynamic, expanding one. Instead, they tried to modify the theory itself, proposing that the gravitational force might become repulsive at extremely large distances. This change wouldn't significantly affect the predicted motion of the planets, but it would allow for an infinite distribution of stars to remain in a stable equilibrium, where the pull from nearby stars was perfectly balanced by the push from distant ones. However, we now believe that such a delicate balance would be fundamentally unstable. You see, if the stars in any particular region happened to drift slightly closer together, the force of their mutual attraction would grow stronger and overcome the repulsive force, causing them to continue collapsing. On the other hand, if the stars moved even slightly farther apart, the repulsive force would dominate, pushing them away from each other at an ever-increasing rate. Another objection to the infinite and static model of the universe is generally credited to the German philosopher Heinrich Olbers, who published a paper on the topic in 1823. In reality, many of Newton's contemporaries had already raised the same issue, and Olbers's article was not the first with serious arguments, just the one that became most widely known. The problem is this. In an endless and unchanging universe, every possible line of sight from your eye should eventually terminate on the surface of a star. Consequently, the entire night sky ought to be as luminous as the surface of the sun. The proposed solution was that the light from these distant stars could be diminished by absorbing matter floating in between. The flaw in this counterargument, however, is that this intervening matter would itself heat up until it glowed just as brightly as the stars it was obscuring. The only way you can avoid the conclusion of a brilliant night sky is to assume that the stars have not been shining for all of eternity, but rather ignited at some finite time in the past. In that scenario, perhaps the light from the most distant stars has not yet reached us. This line of reasoning, of course, brings you to the ultimate question. What caused the stars to ignite in the first place? The problem of the universe's origin is one that has occupied human minds for a very long time. It is worth noting that many early cosmogonies and the creation myths of the Judeo-Christian Muslim traditions also held that our universe began at a specific and not incomprehensibly distant moment in the past. One of the driving forces behind such thinking was the search for a first cause to explain why the universe exists at all. While every single event within the cosmos can be traced back to a preceding cause, the existence of the universe as a whole seems to demand an initial beginning. Another perspective was offered by St. Augustine, who is regarded as blessed by the Orthodox Church and a saint by Catholics. He observed that civilization is always advancing, and we retain memories of who achieved certain milestones or invented particular things, making it improbable that humanity, and by extension the universe, has been around for an eternity. Augustine found the creation date suggested by the Book of Genesis, approximately 5,000 years before our era, to be a plausible timeline. It's fascinating to note that this date is not drastically different from the end of the last ice age, which occurred about 10,000 years before our era, and is what archaeologists generally mark as the starting point of civilization. In contrast, Aristotle and the majority of Greek philosophers rejected the notion of a universe that was created, as it seemed to necessitate divine intervention. They held the belief that both humanity and the surrounding world had existed eternally and would persist forever. To counter the argument about the progress of civilization, these ancient thinkers proposed a cycle of periodic floods and other major disasters that would repeatedly return humanity to a primitive state. This question of whether the universe originated at a specific moment in time and space was later explored exhaustively by the philosopher Immanuel Kant. In his monumental and rather dense 1781 work, The Critique of Pure Reason, he labeled such problems as antinomies, or contradictions of pure reason, because he felt that neither position could be definitively proven or refuted. Kant perceived a fundamental paradox: the thesis, which claims the universe must have a beginning, and the antithesis, which posits that it has always existed. Both seemed logically defensible. He supported the thesis by arguing that if the universe lacked a beginning, an infinite stretch of time would precede every event, a concept he found absurd. Conversely, for the antithesis, he reasoned that if the universe did have a beginning, an infinite period of time must have come before it, which begs the question of why the universe appeared at one particular instant and not another. In truth, Kant's reasoning for both the thesis and the antithesis is essentially identical, as each is built on the premise of an infinite past, whether or not the universe itself has always been there. As we are about to see, the very concept of time becomes meaningless prior to the universe's beginning. St. Augustine was actually the first to articulate this idea when he was asked what God was occupied with before creating the universe. He famously did not give the flippant answer that God was preparing hell for people who ask such questions, but instead stated that time is a property of the universe God made, and thus time itself did not exist before creation. For most of history, when people assumed the universe was static and unchanging, the question of its origin was confined to the realms of metaphysics and theology. Every observable phenomenon could be accounted for by a theory where the universe existed eternally, or by one where it was brought into being at a specific time, but carefully arranged to appear as if it had been there forever. However, a revolutionary discovery was made in 1929 by Edwin Hubble. He observed that, regardless of which direction he looked, distant galaxies were all rushing away from us at high speeds, which meant the universe is expanding. This expansion implies that in the past, all objects in the cosmos were situated much closer to one another. Following this logic, there must have been a moment, roughly 10 or 20,000 million years ago, when everything was concentrated at a single point, resulting in a universe of infinite density. Hubble's breakthrough effectively shifted the question of the universe's origin from philosophy into the domain of science. His observations pointed to a moment known as the Big Bang, when the universe was infinitesimally small and immeasurably dense. Under such extreme conditions, all the established laws of science collapse, rendering them incapable of predicting the future. If any events did take place before the Big Bang, they are irrelevant to us because they could not influence our present reality, and thus they can be dismissed from consideration. It is therefore logical to consider the Big Bang as the commencement of time itself, in the sense that any earlier moments are simply not defined. It is important for you to understand that this type of beginning is fundamentally different from those previously imagined. In a universe that was unchanging, its beginning would have to be initiated by some force external to it, as there would be no inherent physical reason for it to start. With an expanding universe, however, there may well be physical laws that necessitate a beginning. You could still maintain that God created the universe at the instant of the Big Bang, or even at some point after, but it becomes illogical to suggest that creation happened before the Big Bang. An expanding universe does not eliminate the possibility of a creator, but it does place firm constraints on when that creative act could have occurred. Before we can delve deeper into the nature of the universe and whether it had a beginning or will have an end, it's essential for us to agree on what a scientific theory is. I will be using a very straightforward definition. A theory is a model of the universe, or a limited part of it, combined with a set of rules that connect the quantities in that model to the observations we make. This model exists only within our minds and has no independent reality, whatever that term might even mean. A good theory must meet two conditions. First, it must accurately describe a broad class of observations based on a model that contains only a few arbitrary elements. Second, it must make concrete predictions about the outcomes of future observations, which is precisely where Aristotle's theory that everything is made of earth, air, fire, and water, though simple, ultimately failed. In contrast, Newton's theory of gravity was founded on a more straightforward concept, where objects pull on each other with a force linked to a property known as their mass. This model, for all its simplicity, yielded remarkably accurate predictions. According to Newton's law, the gravitational attraction between any two objects is directly related to their masses and weakens with the square of the distance separating them, a principle that flawlessly forecasts the movements of the sun, the moon, and the planets. It's important for you to understand that any physical theory is inherently provisional. It is a hypothesis that can never be truly proven, regardless of how many experiments validate its predictions. You can never be completely sure that a future experiment won't expose a flaw. As the philosopher of science Karl Popper pointed out, a theory can, however, be definitively disproved by a single observation that contradicts its forecasts. The hallmark of a robust theory is its ability to make predictions that are, in principle, testable and capable of being proven false. Each time a new experiment aligns with a theory's predictions, our confidence in it grows, and the theory proves its worth. Yet, if just one observation runs contrary to the theory, we are compelled to either modify it or discard it entirely. This, at least, is the established scientific process, though you could always raise questions about the skill of the individuals performing the experiment. In reality, scientific advancement often sees a new theory emerge as a more refined version of its predecessor. For instance, highly precise measurements of Mercury's orbit showed subtle irregularities that Newton's theory of gravity couldn't quite explain. Einstein's general theory of relativity, however, predicted these slight deviations perfectly. The alignment of Einstein's forecasts with the observed data, where Newton's fell short, was a crucial confirmation of his new theory. Even so, we continue to use Newton's theory in practical applications because, for most situations we face, its results are nearly identical to those from general relativity, and it has the considerable advantage of being much simpler mathematically. The ultimate aspiration of science is to develop a single, comprehensive theory that can account for the entire universe. To tackle this monumental task, most scientists approach it in two stages. The first stage deals with the laws that dictate how the universe evolves over time, allowing us to predict its future state if we know its condition at any given moment. The second stage addresses the more fundamental problem of the universe's initial state. Some thinkers propose that science should only engage with the first part, leaving the question of initial conditions to metaphysics or religion. They argue that an omnipotent God could have initiated the universe in any manner imaginable, which would imply that its evolution could have been completely arbitrary. Yet, the evidence suggests that the universe operates according to very specific and consistent laws, which makes it just as plausible to assume that its initial state was also governed by a set of foundational principles. Because formulating a theory that encompasses the entire universe at once is profoundly challenging, we instead divide the problem into smaller, manageable parts and construct partial theories. Each of these theories describes and predicts a specific range of phenomena, either by ignoring other influences or by representing them with a few simple numbers. This method might be fundamentally flawed. If every aspect of the universe is deeply interconnected, analyzing its components in isolation may never lead to a complete understanding. Nonetheless, this piecemeal approach is responsible for all scientific progress to date. Newton's theory of gravity serves as a perfect example of this, as the gravitational force between two objects depends only on their mass, not on their material composition. This allows you to calculate planetary orbits without needing a detailed theory about the structure of the planets or the Sun. Today, our understanding of the universe rests on two great partial theories: general relativity and quantum mechanics, both products of extraordinary intellectual achievement in the early 20th century. General relativity governs the force of gravity and the large-scale structure of the cosmos, from a few kilometers up to the observable universe's expanse of 1,000,000,000,000,000,000 kilometers. Quantum mechanics, conversely, applies to phenomena on unimaginably small scales, like 1/1,000,000th of a centimeter. The critical issue is that these two theories are mutually exclusive. They cannot both be entirely correct. Consequently, one of the foremost challenges in modern physics is the search for a new, unifying theory, a quantum theory of gravity. If you accept that the universe operates according to consistent laws rather than by chance, then it follows that all partial theories must ultimately merge into a single complete theory that describes everything. Yet, this pursuit of a unified theory presents a deep paradox. Our entire discussion of scientific theories is based on the assumption that we are rational beings who can observe the universe and form logical conclusions. From this standpoint, it seems reasonable that we can gradually approach an understanding of the laws that govern everything. However, if a truly unified theory does exist, it must also govern our own actions. This means the theory itself would have to dictate the outcome of our search for it. Why then would this theory ensure that our observations lead us to the correct conclusions? What would prevent it from guiding us toward incorrect answers, or perhaps from allowing us to reach any conclusion at all? To address these questions, I can provide only a single explanation, which is rooted in Darwin's principle of natural selection. My view is that within any population of self-replicating organisms, there will always be inevitable genetic and environmental differences among individuals. Consequently, some are simply more adept than others at forming accurate conclusions about their surroundings and taking appropriate action, granting them a higher probability of survival and reproduction. As a result, their modes of thought and behavior tend to become the most prevalent in the population. In our history, intelligence and a talent for scientific discovery clearly provided a survival advantage, although it is highly debatable whether this holds true today, as our own scientific advancements could very well lead to our destruction. Even if we avoid that fate, a complete unified theory is not likely to meaningfully improve our survival odds. Still, because the universe operates according to consistent patterns, it's logical to assume that the reasoning abilities we've developed through natural selection would steer us toward finding a complete, unified theory and help us discard incorrect ideas along the way. The partial theories we already possess are effective enough to yield precise predictions in all but the most extreme circumstances, so the pursuit of a final theory is not driven by any practical urgency. You could have made similar arguments against relativity and quantum mechanics. Yet those theories went on to spark revolutions in nuclear physics and microelectronics. Therefore, discovering a complete unified theory might not aid our survival, or even alter the fabric of our daily lives in any significant way. Nevertheless, since the very beginning of civilization, people have been unsettled by events that seem disconnected and lack explanation, compelling them to passionately seek the underlying order of our world. We still have a profound desire to understand why we are here and from where we originated. This innate human thirst for knowledge serves as all the justification needed to continue our quest. Our ultimate objective is nothing less than a complete and total description of the universe we occupy. The modern conception of the laws that dictate the movement of objects has its origins with Galileo and Newton. Prior to their work, the predominant viewpoint was Aristotle's, who proposed that the natural state for any object was to be at rest. He believed that objects only moved when subjected to a force or an impulse. Aristotle also asserted that the universe's fundamental laws could be worked out through pure thought alone, making observational testing unnecessary, which is why, for centuries, nobody actually verified if objects of different weights fall at different speeds. Legend has it that Galileo proved Aristotle's theory false by dropping objects of varying weights from the Leaning Tower of Pisa. This account is almost certainly a myth. But Galileo did conduct a comparable experiment by rolling balls of different weights down a polished, inclined ramp. This setup is a practical alternative to dropping objects from a great height, as the slower speeds make observation much easier. His measurements revealed that every object's speed increases at an identical rate, irrespective of its weight. To illustrate, if you were to roll a ball down a plane that drops 1 meter for every 10 meters of length, its speed would be 1 meter per second after 1 second, then 2 meters per second after 2 seconds, and so on. A lead weight will, of course, fall faster than a feather, but this is solely because the feather experiences much greater slowing from air resistance. If you drop 2 objects where air resistance is insignificant, like 2 lead weights with different masses, you will see them fall at precisely the same rate. Newton formulated his laws of motion based on the measurements Galileo gathered from his inclined plane experiments. In those trials, the same force, the object's own weight, was constantly acting on the object, causing its speed to steadily increase. This led Newton to the insight that a force changes an object's speed rather than simply initiating its movement as was previously believed. This also implied that in the absence of any force, an object will travel in a straight line at a constant velocity, a principle Newton first articulated clearly in his work, Mathematical Principles of Natural Philosophy, published in 1687, and now known as Newton's first law. Newton's second law describes what occurs when a force does act on an object. It will accelerate, meaning it will change its speed, at a rate that is directly proportional to the strength of the force. If you double the force, for instance, you also double the acceleration. The law also states that this acceleration is inversely proportional to the object's mass. A larger mass results in smaller acceleration. As everyone knows from cars, a more powerful engine generates greater acceleration, but that same engine will produce less acceleration in a heavier vehicle. Beyond his laws of motion, Newton also uncovered the law that governs the force of gravity. This law posits that every object in the universe attracts every other object with a force that is proportional to their respective masses. This means, if you double the mass of one object, say object A, the attractive force between it and another object will also double. You can visualize this by imagining the new, larger object A is made of 2 bodies of the original mass, each pulling on object B with the original force, resulting in a total force that is twice as strong. Consequently, if one body's mass were doubled and the others were tripled, the force between them would be 6 times greater. Now it becomes clear why all objects fall with the same acceleration. An object with twice the weight is pulled downward by a gravitational force that is twice as strong, but it also possesses twice the mass. According to Newton's second law, these 2 effects precisely counteract one another. The greater force is exactly what's needed to accelerate the greater mass at the same rate, which is why the acceleration remains constant for all objects, regardless of their weight. Newton's law of gravity establishes that the force between any 2 objects diminishes as the distance between them grows. This principle dictates that if you double the distance from a star, its gravitational influence on you drops to exactly 1/4 of its previous strength. The incredible precision of this law is what allows us to calculate the orbits of the Earth, the Moon, and the other planets with such remarkable accuracy. If the force of gravity weakened more sharply with distance than Newton's law describes, planets would be unable to maintain stable elliptical paths, and would instead spiral into the sun. In the opposite scenario, if gravity's influence decreased more slowly over distance, the collective pull from faraway stars would overwhelm the gravitational hold of our own planet. Aristotle's perspective on motion was fundamentally different from that of Galileo and Newton, as he proposed that an object's natural tendency was to be at rest. He believed that any body would eventually come to a stop unless a force was actively propelling it, and he specifically considered the Earth to be stationary. In direct contrast, Newton's laws suggest that no absolute standard of rest exists anywhere in the universe. This means you could just as validly assert that object A is stationary, while object B moves past it at a steady velocity, as you could claim that B is at rest and A is in motion. For instance, if you disregard the Earth's spin and its orbit for a moment, you can say either that the Earth is still and a train is traveling north at 90 kilometers per hour, or that the train is motionless while the Earth moves south beneath it at 90 kilometers per hour. Should you conduct experiments with moving objects inside that train, you would discover that all of Newton's laws apply perfectly. If you were to play table tennis on board, for example, the ball would behave exactly as predicted by Newton's laws, just as it would on a table beside the tracks. There would be no experiment you could perform to determine whether it was the train or the Earth that was actually moving. A major consequence of having no absolute standard for rest is that you can never definitively say two events that happened at different times occurred in the exact same location in space. Imagine a passenger on the train drops a ball which bounces on a table and returns to their hand 1 second later. From the perspective of an observer on the ground, the 2 points where the ball struck the table are separated by about 40 meters, the distance the train covered during that second. This illustrates that, contrary to Aristotle's view, no event has an absolute position in space. The specific location of events and the distances between them appear different to an observer on the train compared to one standing by the tracks, yet there is no basis for preferring one observer's measurements over the others. This absence of a fixed position, or what was termed absolute space, deeply disturbed Newton because it seemed to contradict his belief in an absolute God. Despite the fact that this conclusion arose directly from his own laws of motion, Newton refused to accept the non-existence of absolute space. This intellectual resistance drew sharp criticism from many, including the philosopher Bishop Berkeley, who argued that all material objects, along with space and time themselves, are merely illusions. It is famously said that upon hearing this, the writer Samuel Johnson kicked a large stone and proclaimed, "I refute it thus." Both Aristotle and Newton, however, shared a firm belief in the concept of absolute time. They were convinced that the duration between any two events could be measured with complete certainty, yielding the same result for any observer equipped with a precise clock. Time, in their view, was a universal constant, entirely separate from and unaffected by space, a perspective that aligned with most people's everyday intuition. However, this common-sense understanding of space and time had to be revised. While it works perfectly well for slow-moving things like apples and planets, it completely breaks down for objects moving at speeds close to that of light. The realization that light travels at a finite, though incredibly high speed, was first demonstrated in 1676 by the Danish astronomer Ole Christensen Romer. Romer achieved this by observing the moons of Jupiter and noticing that the time intervals between their eclipses were not consistent. He saw that the eclipses appeared later when Earth was farther away from Jupiter, and concluded that this discrepancy was due to the extra time light needed to travel the greater distance to reach us. This simple, elegant argument proved that the speed of light was not infinite. Although Roemer's measurements of the Earth-Jupiter distance were not perfectly accurate, leading him to calculate the speed of light as 140,000 miles per second instead of the modern value of 186,000 miles per second. His accomplishment was extraordinary. He not only proved that light has a finite speed, but also managed to measure it, a full 11 years before Newton published his landmark Principia Mathematica. A complete theory of light propagation would not appear until 1865, when the physicist James Clerk Maxwell successfully unified the existing theories of electricity and magnetism. Although Roemer's measurements of the Earth-Jupiter distance were not perfectly accurate, leading him to calculate the speed of light as 140,000 miles per second, instead of the modern value of 186,000 miles per second. His accomplishment was extraordinary. He not only proved that light has a finite speed, but also managed to measure it, a full 11 years before Newton published his landmark Principia Mathematica. A complete theory of light propagation would not appear until 1865, when the physicist James Clerk Maxwell successfully unified the existing theories of electricity and magnetism. Maxwell's equations revealed that intertwined electric and magnetic fields can generate disturbances that propagate as waves at a fixed velocity, similar to how ripples spread across water. We classify these waves by their wavelength, which is the span between two consecutive crests. When this distance is a meter or greater, you are observing radio waves. As the wavelengths shorten into the centimeter range, we call them microwaves, and they become infrared waves down to a scale of 10,000 centimeters. The light you can see has an incredibly small wavelength, just around 4 to 8 millionths of a centimeter, while even more compact wavelengths characterize ultraviolet, X-ray, and gamma rays. A key prediction of Maxwell's theory was that both light and radio waves move at an unchanging speed. This created a puzzle, because Newtonian physics had discarded any concept of a fixed, absolute frame of rest, making it unclear what this constant speed was being measured against. To resolve this, scientists proposed a hypothetical substance known as the ether, which was thought to permeate all of space, including vacuums. The idea was that light waves traveled through this ether in the same way sound waves travel through air, with their speed being constant relative to this medium. Consequently, your own velocity through the ether should alter the speed at which you perceive light approaching. Specifically, this ether theory implied that as the Earth orbits the Sun, the speed of light you measure should be faster when looking in the direction of our planet's motion, compared to when you measure it perpendicularly. In 1887, a remarkably precise experiment was conducted in Cleveland by Albert A. Michelson, who would go on to be the first American Physics Nobel laureate, and his colleague, Edward Morley. They meticulously compared the speed of light along the direction of Earth's travel against its speed at a right angle, and what they discovered was astounding. The two speeds were identical. In the years between 1887 and 1905, scientists, including the prominent Dutch physicist Hendrik Lorentz, tried to reconcile the Michelson-Morley findings by proposing that objects moving through the ether physically shrink and their clocks run slower. Then, in 1905, a little-known Swiss patent office employee named Albert Einstein released a landmark paper arguing that the ether itself was redundant. The only thing you had to give up, he claimed, was the idea of absolute time. Just weeks after, a leading French mathematician, Henri Poincaré, articulated a similar conclusion, with Einstein's reasoning being more rooted in physics and Poincaré's in mathematics. Though Einstein is generally celebrated as the theory's originator, Poincaré's work was also vital to its key developments. The core tenet of this new framework, which came to be known as relativity, was that the fundamental laws of science must apply equally to you and any other observer in free motion, irrespective of your velocity. While this principle already held for Newton's laws of motion, it was now being applied to Maxwell's theory, and, most critically, to the speed of light. This means that no matter how fast you are traveling, you will always measure the speed of light to be exactly the same. From this one straightforward idea, several extraordinary implications arise, with the most famous being the equivalence of mass and energy, captured in Einstein's celebrated equation, E equals mc squared. In this formula, where E represents energy, m stands for mass, and c is the speed of light, the core idea is that an object's kinetic energy effectively contributes to its total mass. To put it another way, the greater an object's energy, the more difficult it is to make it go faster. You would only notice this effect becoming significant as an object approaches the velocity of light. For instance, at 10% of light speed, an object's mass grows by a mere 0.5%. However, if you accelerate that same object to 90% of light speed, its mass actually doubles. As you get closer and closer to the speed of light, this mass increase becomes astronomical, demanding ever-increasing amounts of energy for any additional acceleration. Ultimately, an object can never attain the speed of light because its mass would become infinite at that point. Because mass and energy are two sides of the same coin, this would necessitate an infinite supply of energy. Therefore, the principle of relativity dictates that any object with mass is permanently restricted to speeds below that of light, a velocity reserved only for light and other waves that have no inherent mass. Another profound outcome of relativity is its complete transformation of how we perceive space and time. In Newtonian physics, if you were to send a beam of light from one location to another, all observers would agree on the duration of its journey, because time was considered absolute. Yet, they could disagree on the distance it covered, since space was not absolute. This leads to a contradiction, because if speed is distance divided by time, different observers would calculate different speeds for light. Relativity resolves this by insisting that everyone must measure the same speed of light. If you and I agree on the speed, but disagree on the distance, it logically follows that we must also disagree on the time it took to travel that distance. So, the duration of the journey becomes the disputed distance divided by the agreed-upon speed of light. What this means is that relativity completely dismantles the notion of a single, universal time. Instead, you must have your own personal experience of time, which you would measure with your own clock. Consequently, the readings on identical clocks can differ if you and another observer are in motion relative to each other. You can pinpoint the location and moment of any event by using a radar-like technique, by sending out a light or radio pulse and timing how long it takes for the reflection to come back to you. The moment an event occurs is calculated as the midpoint between when a pulse is transmitted and when its reflection is received. Consequently, the distance to that event is simply half of this total round-trip duration multiplied by the speed of light. Here, I'm using the term event to describe something that takes place at a single point in space and a single instant in time. Using this method, observers who are in motion relative to one another will inevitably assign different times and locations to the very same event. It's crucial to understand that none of these individual measurements is inherently more correct than any other. They are, however, all mathematically related. Any observer can work out the precise time and position that another observer will record for an event, as long as they know the second observer's relative speed. This is precisely the technique we employ today for highly accurate distance measurements. because our ability to measure time has far surpassed our ability to measure length. Even the meter itself is now formally defined as the distance light travels in 0.0000003356400952 seconds, as measured by atomic cesium clocks. This specific value was chosen to align with the historical definition of a meter, which was the distance between two markings on a particular platinum bar stored in Paris. We could also adopt a more intuitive unit of length, called a light second, which is simply the distance that light covers in 1 second. In the framework of relativity, distance is defined through time and the speed of light, which means that every observer will, by definition, measure the exact same speed for light. 1 meter per 0.0000003356400952 seconds. This new understanding completely eliminates the need for the hypothetical ether, a substance whose existence the Michelson-Morley experiment famously failed to detect. However, embracing relativity requires us to fundamentally alter our perception of space and time. We must accept that time isn't a separate, independent entity that flows uniformly for everyone. Instead, it is intrinsically linked with space, merging to create a single, unified construct that we call spacetime. From our daily lives, you know that we can describe the location of any point in space with 3 numbers, which we call its coordinates. For instance, I could specify a spot in a room as being 2 meters from one wall, 1 meter from another, and 1.5 meters above the floor. Alternatively, you could define a location on the globe by its latitude, longitude, and altitude above sea level. You are free to use any 3 appropriate coordinates, although their practical application is always limited. No one, for example, would attempt to specify the moon's position by its distance in kilometers north and west of Piccadilly Circus and its height above the ground. Instead, we might describe its location using its distance from the sun, its distance from the plane of the planet's orbits, and the angle between the moon-sun line and the line to a nearby star like Alpha Centauri. Even these coordinates would be ill-suited for pinpointing the sun's position within our galaxy, or our galaxy's position among its cosmic neighbors, forcing us to map the universe in overlapping patches, each with its own local coordinate system. An event is something that occurs at a specific place and a specific time, so we can characterize it fully with 4 numbers, 3 spatial coordinates, and 1 time coordinate. Following this logic, the 4 coordinates of any given event can be seen as defining its position within a 4-dimensional space known as space-time. While I find it difficult enough to truly picture 3-dimensional space, and a 4-dimensional one is impossible for us to visualize, we can make it more accessible through simpler diagrams. Consider how we can easily draw a 2-dimensional space, like the surface of the Earth, where any point's position can be fixed by just 2 coordinates, latitude and longitude. In spacetime diagrams, we often represent the time axis vertically, while the spatial axes are shown horizontally. Imagine a chart where the distance from the Sun to the star Alpha Centauri is plotted along the horizontal axis in miles, and time is measured upward along the vertical axis in years. We have established that Maxwell's equations, which are confirmed by precise measurements, predict that the speed of light remains constant regardless of the source's motion. This has a fascinating consequence. A pulse of light emitted at a particular moment from a specific point in space will expand outward as a growing sphere of light. After 1/1,000,000th of a second, this sphere of light will have a radius of 300 meters. After 2/1,000,000ths of a second, the radius will double to 600 meters, and so it continues. This process is much like the ripples that spread across a pond's surface after a stone is thrown in. Those ripples form a circle that expands with time. If you imagine a three-dimensional model, with the pond's 2 dimensions plus a third for time, the expanding circle of water actually traces out a cone whose tip is at the exact place and time the stone hit the water. In a similar way, light spreading out from an event in 4-dimensional spacetime creates a 3-dimensional cone, which is known as the event's future light cone. We can also envision another cone, called the past light cone, which represents the complete set of all events from which a pulse of light could have traveled to reach the event in question. Together, an event's past and future light cones divide all of spacetime into 3 distinct regions. The area inside the future light cone is the event's absolute future, the set of all points in spacetime that can possibly be affected by what happens at that event. Events outside this light cone cannot be reached by signals from the event, since nothing can exceed the speed of light, and therefore they remain entirely unaffected. The region contained within the past light cone constitutes the event's absolute past. This is the collection of all events from which signals, traveling at or below the speed of light, could have journeyed through spacetime to arrive at our present event. Anything that occurs in this region has the potential to influence what is happening right here, right now. Essentially, the past light cone encompasses every event that possesses the potential to affect what occurs at a specific point in space-time. If you had knowledge of everything happening at a single moment within this cone's boundaries, you could accurately forecast the outcome at that particular event. The area of spacetime that exists outside of both the past and future light cones is referred to as the elsewhere, a region where events can neither influence nor be influenced by what unfolds at your point of observation. To give you a practical example, imagine if the sun were to suddenly extinguish this very second. The consequences would not be felt on Earth instantly, as our planet would momentarily reside in the elsewhere region relative to the sun's final moment. You would only become aware of this cosmic event 8 minutes later, which is precisely the time it takes for light to traverse the distance from the sun to us. It is only at that point that events on Earth would finally cross into the future light cone of the sun's extinguishment. This same principle explains why you cannot know what is transpiring at this exact moment in the far reaches of the cosmos. The light that reaches you from distant galaxies was sent on its journey millions of years ago, and light from the most remote objects we can detect has traveled for 8 billion years. Consequently, whenever you gaze at the universe, you are actually looking at a snapshot of its distant past, not its present state. When you disregard the influence of gravity, a step taken by both Einstein and Poincaré in 1905, you arrive at the theory known as special relativity. This framework allows you to construct a light cone for any event in spacetime, which maps out all the potential trajectories for light emanating from that point. Because the speed of light is constant for all events and in all directions, every light cone is perfectly identical and aligned in the same way, establishing a universal speed limit that confines the path of any object within these cones. Special relativity provided a brilliant explanation for the constant speed of light observed by all, a fact confirmed by the Michelson-Morley experiment, and it accurately detailed the behavior of objects moving at near light speeds. However, this new understanding clashed directly with Newton's theory of gravity, which proposed that objects exert an attractive force on each other dependent on their separation. Such a model implied that moving one object would instantaneously alter the force on another, suggesting that gravitational effects must travel at an infinite speed, a concept forbidden by the constraints of relativity. Between the years of 1908 and 1914, Einstein engaged in several unsuccessful efforts to formulate a theory of gravity that could be reconciled with special relativity. It wasn't until 1915 that he finally published his masterpiece, now known as the general theory of relativity. His proposal was revolutionary. He suggested that gravity isn't a force at all, but rather a manifestation of spacetime itself being curved by the presence of mass and energy, contrary to the long-held assumption that it was flat. Objects like the Earth, therefore, are not being compelled into curved orbits by a gravitational pull. Instead, they are traveling along the most direct routes possible through warped spacetime. These paths are known as geodesics, which represent the shortest, or sometimes longest, distance between two adjacent points. For instance, on the curved two-dimensional surface of our planet, geodesics take the form of great circles, which are the most efficient routes between any two locations, a principle airline pilots use every day. According to general relativity, all objects move in straight lines within four-dimensional spacetime. But to you, these paths appear bent within your perception of three-dimensional space. Consider watching an airplane fly over a rugged, hilly landscape. While the plane maintains a straight trajectory in 3 dimensions, its shadow on the two-dimensional ground below follows a curved path. Similarly, the Sun's immense mass warps spacetime in such a way that Earth, while following a straight line in 4 dimensions, appears to us to trace a circular orbit in 3. The planetary orbits calculated by general relativity are nearly identical to those derived from Newton's theory of gravity. Yet, for Mercury, the planet closest to the Sun with a highly elliptical orbit and the strongest gravitational influence, general relativity predicts that the ellipse's long axis should rotate around the Sun at a rate of about 1 degree every 10,000 years. This tiny but significant effect had actually been observed before 1915, serving as a powerful early confirmation of Einstein's theory. More recent radar data has shown similar, subtle deviations from Newtonian predictions in the orbits of other planets, all of which align perfectly with general relativity. This theory also dictates that rays of light must follow the geodesics of curved spacetime, which means that light itself no longer travels in perfectly straight lines, but instead bends in the presence of a gravitational field. The light cones of points in close proximity to the Sun, for example, should be slightly warped by its mass. This implies that light from a distant star passing near the Sun will be deflected by a small angle, causing an observer on Earth to perceive the star in a slightly different position from its true location. Of course, if a star's light were always deflected by the Sun, you would have no way of knowing whether the light was bending or if the star was simply located where you see it. However, as Earth revolves around the Sun, different stars continuously pass behind it, causing their light to be deflected and their apparent positions to shift relative to other stars. Observing this phenomenon is extremely challenging under normal circumstances, because the Sun's brilliance completely washes out the faint starlight. The ideal opportunity arises only during a total solar eclipse, when the Moon perfectly blocks the Sun's disk. But in 1915, with the First World War raging, no one could immediately set out to verify this profound prediction. It wasn't until 1919 that the theory's prediction of light bending around the Sun was finally demonstrated by a British expedition observing a solar eclipse in West Africa. The confirmation of a German-born theory by British scientists was celebrated as a powerful gesture of reconciliation between the two nations following the war. However, A later analysis of the expedition's photographs showed that the measurement errors were as large as the effect they were trying to measure. This suggests the British team's result was either a stroke of luck or an instance of researchers finding the outcome they expected. Nevertheless, the deflection of light by the sun has since been confirmed with great precision by numerous subsequent observations. Another core prediction of general relativity is that time itself should pass more slowly near a massive object like our planet. This idea stems from the connection between the energy of light and its frequency, which is the number of light waves that pass per second. As energy increases, so does frequency. When light travels upward against Earth's gravitational field, it loses energy, causing its frequency to drop. For an observer positioned at a higher altitude, this means everything happening below them would seem to unfold at a slower pace. This very prediction was put to the test in 1962 with a pair of highly accurate clocks, one situated at the base of a water tower and the other at its top. As general relativity anticipated, the clock closer to the Earth ran slower. Today, this difference in the rate of time at varying heights is critically important, especially with the development of precise navigation systems that depend on satellite signals. If these calculations failed to account for the predictions of general relativity, your coordinates would be off by several kilometers. Just as Newton's laws of motion did away with the idea of an absolute position in space, relativity liberated us from the concept of absolute time. Imagine a set of twins. If one goes to live on a mountaintop while the other remains at sea level, the twin at the higher altitude will age more quickly. Upon reuniting, one would be visibly older. While this age difference would be tiny, it would become far more pronounced if one twin undertook a long voyage in a spacecraft traveling near the speed of light. That twin would return to find they were much younger than the sibling who stayed on Earth. This is known as the twin paradox, though it's only a paradox if you hold on to the outdated belief in a single, absolute time. In the framework of general relativity, there is no universal clock. Instead, every individual experiences their own personal timeline, which is shaped by their location and motion. Before 1915, space and time were viewed as a fixed backdrop where events occurred without affecting the stage itself. Even special relativity maintained this notion. Bodies moved and forces acted, but space and time were passive constants. It seemed natural to assume that space and time were simply infinite. General relativity completely overturned this view, revealing that space and time are dynamic quantities. When a body moves or a force acts, it alters the curvature of spacetime, and this altered structure of spacetime then dictates how bodies move and forces behave. Space and time not only influence everything that happens in the universe, but they are also shaped by everything within it. Just as you cannot discuss events in the universe without the concepts of space and time, general relativity makes it nonsensical to speak of space and time as existing independently of the universe. Over the following decades, this profound new understanding of space-time would completely reshape our perception of the cosmos. The old model of a mostly static universe that might have existed forever was replaced by the vision of a dynamic, expanding cosmos that seems to have begun at a specific moment in the past and may well end at some point in the future. On a clear, moonless night, the most brilliant objects you are likely to see in the sky are the planets Venus, Mars, Jupiter, and Saturn. You will also notice a tremendous number of stars, which are much like our own sun, but located at immense distances. As the Earth completes its orbit around the Sun, some of these so-called fixed stars appear to shift their positions slightly in relation to each other. They are not, in fact, stationary. This apparent movement occurs because some stars are closer to us than others, and as we orbit the Sun, these nearer stars seem to drift against the backdrop of the more distant ones. This phenomenon allows us to measure the distance to these stars directly. The more pronounced their apparent shift, the closer they are to us. The nearest star, Proxima Centauri, is located about 4 light-years away, which means its light travels for approximately 4 years, or a distance of about 37 trillion kilometers, before reaching us. In contrast, most stars that are visible to the naked eye are hundreds of light-years distant, while our own Sun is a mere 8 light-minutes away from Earth. The stars you can see are spread across the celestial sphere, yet they appear particularly concentrated in a band we identify as the Milky Way. As far back as 1750, some astronomers proposed that the Milky Way's appearance could be explained if most visible stars are part of a single, massive, disc-shaped structure, what we now understand to be a spiral galaxy. Decades later, the astronomer William Herschel lent support to this idea by undertaking the colossal project of cataloging the positions and distances of countless stars, though the concept would not be universally accepted until the early 20th century. Our modern picture of the universe finally began to crystallize in 1924, when the American astronomer Edwin Hubble proved that our galaxy is not alone. He demonstrated the existence of many other galaxies, all separated from one another by enormous expanses of empty space. This discovery established that our own Milky Way is just one of countless galaxies scattered throughout the cosmos, fundamentally changing our place within it. To substantiate his theory, Hubble first needed to calculate the distances to various galaxies. These cosmic islands are so remote that their positions in the sky appear fixed, unlike nearby stars, which forced Hubble to devise indirect measurement techniques. A star's apparent brightness is governed by 2 things: its intrinsic luminosity, the actual amount of light it produces, and its distance from you. For stars in our cosmic neighborhood, we can measure both their brightness and distance, allowing us to calculate their true luminosity. Hubble realized that if he knew the intrinsic luminosity of stars in other galaxies, he could determine their distance simply by measuring how bright they appear to us. He observed that certain star types always possess the same luminosity when they are close enough for a direct measurement. He therefore proposed that if you find one of these standard stars in a distant galaxy, you can assume it has that same luminosity and use it to calculate the galaxy's distance. By performing this calculation for several such stars within the same galaxy and getting consistent results, the distance could be established with confidence, a method he used to measure the distances to 9 different galaxies. Today, we understand that our own galaxy is just one among hundreds of billions of others that are visible with our modern telescopes. And each of those galaxies is home to hundreds of billions of stars. The Milky Way itself spans about 100,000 light-years in diameter. It turns in a slow, majestic rotation, with stars in the spiral arms taking several 100 million years to complete a single orbit around the galactic center. Our Sun is just a typical, medium-sized yellow star, situated on the inner edge of one of these spiraling arms. A far cry from the ancient belief of Aristotle and Ptolemy that the Earth was the center of everything. Because stars are so incredibly far away, they look like simple points of light, making it impossible to see their actual size or shape. So how is it possible for us to even talk about different kinds of stars? For the vast majority of them, the only trait we can actually observe is the color of the light they radiate. Following Newton's discovery that a prism can split sunlight into a rainbow-like spectrum of component colors, we learned to do the same with starlight. By aiming a telescope at a star or galaxy, we can break its light down into a detailed spectrum for analysis. While every star has a distinct spectrum, the overall distribution of colors consistently matches the light from any object heated until it glows. This light, known as a thermal spectrum, has a unique profile that depends only on the object's temperature, which means we can precisely determine a star's temperature just by looking at its spectrum. Furthermore, we observe that very specific colors are missing from these stellar spectra. Since we know that every chemical element absorbs a unique set of colors, we can match these missing bands to known elements and figure out the exact chemical composition of a star's atmosphere. As astronomers in the 1920s began analyzing the spectra of stars in other galaxies, they stumbled upon an even more peculiar finding. The familiar sets of missing colors were present, but the entire pattern was consistently shifted by the same degree toward the red end of the spectrum. To make sense of this, you first need to understand a principle known as the Doppler effect. Visible light, as you know, is composed of waves in the electromagnetic field. The frequency of these waves, the number that pass by per second, is incredibly high, varying from 400 to 700 million oscillations every second. Your eye interprets these different frequencies as different colors, with the lowest frequencies appearing as red and the highest frequencies appearing as violet. Now, picture a light source like a star at a fixed distance from you, emitting light at a steady frequency. In this case, the frequency of the waves you receive is identical to the frequency at which they were sent. Let's now imagine that source starts moving toward you. Because the source is closer each time it emits the next wave crest, the waves arrive more frequently, and you perceive a higher frequency than if the star had remained still. Conversely, if the source is moving away from you, the waves become stretched out, and the frequency you observe is lower. This phenomenon means that the light from stars receding from us is shifted toward lower frequencies, the red end of the spectrum, creating what we call a redshift. In contrast, the light from approaching stars is shifted to higher frequencies, resulting in a blue shift. This connection between velocity and frequency is the Doppler effect, which you encounter in daily life. Think of a car on the highway. As it comes toward you, its engine sounds higher pitched, but as it passes and moves away, the pitch drops. This same principle applies to light and radio waves, and is even used by police to measure a car's speed using reflected radio signals. After establishing that other galaxies truly existed, Hubble devoted years to cataloging their distances and observing their spectra. At the time, the scientific consensus was that galaxies moved randomly, so you should see an equal number of red-shifted and blue-shifted spectra. It was therefore a profound shock when the data showed that the vast majority of galaxies displayed a redshift. This pointed to an astonishing conclusion. Almost every galaxy in the universe is moving away from us. Even more remarkable was the discovery Hubble published in 1929, which revealed that a galaxy's redshift is not arbitrary but is instead directly proportional to its distance from you. To put it simply, the more remote a galaxy is, the more rapidly it is moving away. This finding dismantled the long-held idea of a static cosmos, proving that the universe is in a state of continuous expansion, with the gaps between galaxies perpetually widening. The realization that the universe is expanding stands as one of the most profound intellectual upheavals of the 20th century. In retrospect, you have to wonder why this concept wasn't formulated much earlier. Thinkers like Newton should have deduced that a static universe would inevitably collapse under its own gravitational pull. If you instead imagine an expanding universe, Its ultimate destiny hinges on its velocity. A sufficiently slow expansion would eventually be overcome by gravity, causing it to halt and then contract. However, should the expansion rate surpass a certain critical threshold, gravity would be too weak to stop it, and the universe would expand for eternity. You can visualize this using the analogy of a rocket launching from Earth. If its velocity is relatively low, gravity will ultimately pull it back to the surface. But if the rocket exceeds a critical speed, approximately 11 kilometers per second, it will escape Earth's gravitational field and travel away indefinitely. The universe's expansion could have been inferred from Newton's theory of gravitation as early as the 18th or even the late 17th century. Nevertheless, the belief in an unchanging universe was so deeply rooted that it dominated scientific thought until the early 20th century. Even Albert Einstein was committed to the idea of a static cosmos when he developed his general theory of relativity in 1915. In order to align his theory with this prevailing view, he introduced what he termed the cosmological constant. This modification proposed a new kind of anti-gravitational force, one not produced by any specific source, but inherent to the structure of spacetime itself. Einstein posited that this intrinsic expansion of spacetime would perfectly counteract the gravitational attraction of all matter, resulting in a balanced, static universe. While Einstein and other physicists were trying to find ways to avoid the non-static universe their own theories predicted, it seems only one person fully embraced the implications of general relativity. The Russian physicist and mathematician Alexander Friedmann chose not to circumvent this prediction, but to explain it. He started from two very simple principles. First, that the universe appears identical in every direction you look, and second, that this would be true for any observer at any other point in the cosmos. From these two assumptions alone, Friedmann demonstrated that the universe could not be static. In 1922, years before Hubble's observational proof, Friedmann had already predicted this very outcome with precision. Of course, the notion that the universe looks the same in all directions isn't perfectly accurate on a local level. As you know, the stars of our own galaxy, for instance, form the distinct band of light across the night sky called the Milky Way. However, if you consider the distribution of distant galaxies, you find their numbers are nearly uniform in every direction. This confirms that, on a scale vastly exceeding the distances between galaxies, the universe is indeed approximately the same everywhere. For a long time, this was seen as merely a useful approximation that supported Friedmann's hypothesis. Then, through a remarkable turn of events, it was discovered that his hypothesis was not just an approximation, but an incredibly accurate description of our universe. In 1965, this confirmation came from two American physicists, Arno Penzias and Robert Wilson, who were testing a highly sensitive microwave detector at Bell Laboratories in New Jersey. Microwaves are a form of light with a much lower frequency, vibrating at roughly 10 billion waves per second. During their work, Penzias and Wilson detected that their instrument was registering a higher-than-expected level of noise, a persistent hum that seemed to originate from no particular direction. Their initial efforts to explain the phenomenon involved investigating mundane causes, such as cleaning bird droppings from the antenna. Yet after ruling out every possible source of interference, they found that the excess noise remained constant regardless of where the detector was aimed. They knew that atmospheric noise would be stronger when pointing toward the horizon, as the signal must pass through a thicker layer of air. The uniformity of their signal meant its origin had to lie beyond Earth's atmosphere. The noise level was identical day and night, and throughout the year, unaffected by the Earth's rotation or its orbit around the Sun. This consistency proved its source was not only outside the solar system, but also beyond our own galaxy. Otherwise, its intensity would have shifted as Earth's motion changed the detector's orientation. This radiation, as you now know, travels across almost the entire observable universe. Since this signal is the same from all directions, it follows that the universe itself must be uniform, at least on a very large scale. We now know that this background noise varies by no more than 1/10,000th from one point in the sky to another. Unintentionally, Penzias and Wilson had found stunningly precise verification of Friedman's first assumption. At about the same time, two other American physicists at nearby Princeton University, Bob Dickey and Jim Peebles, were also conducting research on microwaves. They were putting to the test a hypothesis from George Gamow, a one-time student of Friedman, who proposed that the universe in its infancy was immensely hot, dense, and glowed white-hot. Gamow and his team theorized that we should still be able to detect the radiance from this early cosmos, because light from its most distant parts would only now be reaching us. However, the universe's expansion would cause such an extreme redshift in this light that it would arrive today not as visible light, but as microwave radiation. Dick and Peebles were in the process of building an experiment to find this exact radiation when they learned about the work of Penzias and Wilson, who realized they had stumbled upon it already. This discovery earned Penzias and Wilson the Nobel Prize in 1978, a result some consider rather unjust considering the foundational contributions of Dick, Peebles, and especially Gamow. At a superficial glance, the observation that the universe appears uniform in every direction could lead you to think that our position within it holds some special significance. Specifically, because we observe every other galaxy moving away from us, it might seem as though we are positioned at the very center of everything. There is, however, an alternative interpretation. The cosmos would present this same uniform appearance if you were observing it from any other galaxy. This alternative view aligns with Friedman's second fundamental hypothesis, which we accept not because of scientific proof for or against it, but as an act of modesty. It would be incredibly peculiar if the universe appeared isotropic, or the same in all directions, only from our vantage point, and not from any other location. In Friedman's model, every galaxy is receding from every other galaxy, creating a dynamic of universal expansion. Imagine an expanding balloon covered in dots to visualize this concept. As you inflate the balloon, the space between any two dots increases, yet no single dot can be identified as the center of the expansion. Furthermore, the dots that are already far apart from one another will recede at a much faster rate. Friedman's model similarly posits that the velocity at which any two galaxies separate is directly proportional to the distance between them. The model's prediction that a galaxy's redshift should be directly proportional to its distance from us is precisely what Hubble observed. Despite the remarkable success of this model and how well its predictions matched Hubble's data, Friedman's research went largely unnoticed in the Western world until 1935. It was in that year that Howard Robertson, an American physicist, and Arthur Walker, a British mathematician, independently developed similar models in response to Hubble's discovery of the expanding universe. While Friedman himself focused on only one outcome, there are actually three distinct models that satisfy his two basic assumptions. In the first type of model, the one Friedman originally proposed, The universe expands just slowly enough for the gravitational pull among galaxies to decelerate the expansion and ultimately reverse it. The galaxies would then start moving toward each other, causing the universe to contract, with the distance between them going from 0 to a maximum value and back to 0 again. In the second type of model, the universe is expanding so rapidly that gravity, while able to slow it down, can never bring the expansion to a complete halt. The distance between galaxies begins at 0 and increases infinitely, eventually resulting in them moving apart at a steady, constant speed. The third model describes a universe where the expansion rate is precisely the minimum required to prevent a collapse. Here, the distance between galaxies starts at 0 and grows forever, but their speed of separation continually decreases, approaching but never quite reaching 0. A truly fascinating feature of Friedman's first model is that the universe is spatially finite, yet it has no boundaries. Gravity in this scenario is so powerful that it causes space to curve in on itself, in a manner analogous to the surface of the Earth. If you travel in a single direction on Earth's surface, you don't encounter an impassable barrier or fall off an edge. You simply end up back where you started. Friedman's model envisions space in a similar way, but with 3 dimensions instead of 2. In this model, the 4th dimension, time, is also finite, much like a line segment possessing both a beginning and an end. As I will discuss later, when you combine general relativity with the uncertainty principle from quantum mechanics, it becomes possible for both space and time to be finite, without requiring any edges or boundaries. The notion of circumnavigating the entire universe to return to your starting point is a compelling idea for science fiction, but it holds no practical value. It can be demonstrated that the universe would collapse back to 0 size long before you could ever complete such a journey. To make it back to your origin before the universe ends, your travels would have to exceed the speed of light, a feat that is fundamentally impossible. In the first Friedman model, where the universe expands and then contracts, space is positively curved and thus finite. By contrast, the second model of eternal expansion features a negatively curved, infinite space, much like the surface of a saddle. Finally, the third model, which expands at the critical rate, is characterized by a flat and also infinite space. So, the crucial question remains: which of Friedman's models accurately depicts our own universe? Will it one day cease its expansion and begin to contract, or is it destined to expand for eternity? To find the answer, we must determine the current rate of cosmic expansion and the universe's present average density. If the density is below a specific critical value dictated by the expansion rate, then gravitational attraction will be insufficient to halt the expansion. Conversely, if the density exceeds this critical value, gravity will ultimately win, stopping the expansion and triggering a universal contraction. We can figure out the current rate of expansion by measuring the speeds at which other galaxies are receding from us, a task accomplished using the Doppler effect. While these velocity measurements can be performed with great precision, our knowledge of the distances to these galaxies is quite limited because we are unable to measure them directly. Consequently, our best estimate is that the universe is expanding at a rate of 5 to 10% every 1 billion years. The uncertainty surrounding the current average density of the universe is, however, even more pronounced. When you tally the mass of every observable star across our own and other galaxies, the total falls short by a factor of more than 100 of the density needed to stop cosmic expansion, even using the most conservative estimates. We infer the existence of a substantial amount of invisible dark matter in our galaxy and others, based on the gravitational pull affecting stellar orbits. Likewise, since galaxies typically form in clusters, we can deduce the presence of even more dark matter between them by observing their movements. Even after accounting for all this detectable dark matter, the total mass still only reaches about 1/10 of the critical value required to halt the expansion. Of course, we cannot rule out the existence of some other, yet undetected form of matter that is spread evenly throughout the cosmos, which could potentially raise the average density to the level needed to stop everything. Therefore, the evidence available to us strongly indicates that the universe is destined to expand forever. About the only thing I can state with certainty is that even if the universe were to start contracting, this event would not occur for at least another 10 billion years, as it has already been expanding for that duration. This shouldn't cause you too much alarm, because by that distant future, unless we have managed to colonize other star systems, humanity, along with our sun, will have long since vanished. Every version of Friedman's models points to a specific moment in the past, somewhere between 10 and 20 billion years ago, when the space between adjacent galaxies must have been zero. At that instant, which we refer to as the Big Bang, the universe's density and the curvature of spacetime would have been infinite. Because mathematicians are unable to work with infinite numbers in a meaningful way, general relativity itself, the foundation of Friedman's solutions, indicates a point where the theory ceases to apply. Such a point is known as a singularity. All of our scientific theories are constructed upon the premise that space-time is smooth and nearly flat, which means they all break down at the singularity of the Big Bang, where space-time's curvature becomes infinite. Consequently, even if there were events that took place before the Big Bang, they could not be used to forecast what would happen after, as predictability would be lost at that point. By the same token, since all we can know is what has transpired since the Big Bang, we are unable to determine what happened before it. Events preceding the Big Bang hold no consequences for us, and for that reason they shouldn't be included in a scientific model of the cosmos. We should therefore omit them from our model, and treat the Big Bang as the very beginning of time. This concept of time having a definite start is unsettling for many people, perhaps because it hints at an act of divine intervention. The Catholic Church, in contrast, embraced the Big Bang model, officially declaring in 1951 that it aligned with the Bible. Several attempts have been made to devise a model that avoids the Big Bang. The most prominent of these was the steady-state theory, put forward in 1948 by Hermann Bondi, Thomas Gold, and Fred Hoyle. Their idea proposed that as galaxies drift apart, new galaxies are perpetually created from new matter that is constantly coming into existence, resulting in a universe that appears largely unchanged at all times and from all locations. While this concept of continuous matter creation required a modification of general relativity, the rate of creation needed was incredibly low, around 1 particle per cubic kilometer each year, so it didn't create a conflict with experimental observations. The steady-state theory was a robust scientific model. It was simple and made clear predictions that observational tests could verify. One of its core predictions was that the number of galaxies or similar celestial objects within any given volume of space should be constant, regardless of where or when you look. A group of astronomers from Cambridge University, led by Martin Ryle, began compiling a catalogue of radio sources in the sky during the late 1950s and early 1960s. This team demonstrated that the majority of these sources were located outside our own galaxy, and they observed that weaker sources were far more numerous than stronger ones. Interpreting the weak sources as being more distant and the strong ones as closer, they found that there were more sources per unit volume in remote space than in our cosmic neighborhood. This observation could have implied either that we are located at the center of a vast cosmic region with fewer radio sources than elsewhere, or that the universe had more sources in the distant past when the radio waves began their journey to us. Both possibilities contradicted the steady-state theory's predictions. Furthermore, the discovery of cosmic microwave radiation in 1965 provided strong evidence that the universe was indeed denser in its past, which ultimately led to the theory being abandoned. In 1963, another attempt to sidestep the Big Bang and the beginning of time came from two Russian physicists, Yevgeny Lifshitz and Isaac Kalatnikov. They proposed that the Big Bang singularity might only be a characteristic of Friedmann's models, which are, after all, just approximations of the real universe. They argued that in Friedmann's idealized models, galaxies all move directly away from one another, which forces them to originate from a single point in the past, a condition that might not apply to the actual cosmos. You have to understand that in the actual universe, galaxies don't just travel in straight lines away from one another. They also possess minor sideways velocities. This reality suggests that galaxies might not have originated from one exact point in the past. It opens the possibility that they were merely incredibly close together, leading to the idea that our expanding cosmos could have emerged from a preceding phase of contraction, where not all particles collided, but some might have narrowly missed each other and rebounded, initiating the expansion we see today. This raises a crucial question. How can we be certain that the universe actually began with a Big Bang? To investigate this, Yevgeny Lifshitz and Isaac Kalatnikov in 1963 analyzed models similar to Friedmann's, but which incorporated the irregularities and random motions of real galaxies. They demonstrated that these more realistic models could still start with a Big Bang singularity, even without perfect straight-line recession. However, they initially claimed this was a special case, arguing that since the coordinated motion required was so specific, a singular beginning was not a necessary feature of our universe. Later, Roger Penrose and I approached this problem using entirely different mathematical methods. We were able to prove that a singularity was, in fact, unavoidable, provided that general relativity is correct and the universe contains the amount of matter we observe. Our conclusion wasn't dependent on the precise movements of galaxies, but rested on the fundamental principle that gravity is always an attractive force. This work solidified the case for a singular origin, shifting the scientific consensus. Interestingly, the work by Lifshitz and Kalatnikov evolved over time. While they initially argued that non-singular models were far more probable, they later uncovered a much wider category of models where singularities were inevitable, without any need for special galaxy movements. Consequently, by 1970, they had revised their earlier conclusions. Their research was nonetheless profoundly important because it established that, within the framework of general relativity, the universe could have started from a singular point, like the Big Bang. The decisive breakthrough, however, came from the English mathematician and physicist Roger Penrose in 1965. By examining the behavior of light cones in general relativity and the unceasingly attractive nature of gravity, Penrose proved that a collapsing star is inevitably confined to a region whose surface area must eventually diminish to zero. As the surface vanishes, so too must its volume, causing all the star's matter to be crushed into a point of infinite density and spacetime curvature, creating a singularity known as a black hole. At first, Penrose's theorem appeared to apply only to the collapse of stars, and offered no direct insight into the origin of the entire universe. However, after studying his proof, which concludes that any body undergoing gravitational collapse must end in a singularity, it struck me that the theorem would remain valid if time were reversed, turning collapse into expansion. This insight implied that any expanding Friedman-type model of the cosmos must have necessarily begun from a singularity as well, though a technical requirement of Penrose's proof was that the universe had to be spatially infinite. What this reveals is a dramatic transformation in our cosmic perspective, achieved in less than 50 years, which overturned thousands of years of established thought. This revolution started with Hubble's discovery of the expanding universe and the dawning realization of our own planet's insignificance. As more evidence accumulated, it became overwhelmingly clear that the universe must have had a definitive beginning in time. Ultimately, our proof demonstrated that general relativity is an incomplete theory, as it cannot explain how the universe began. According to its own principles, all physical laws break down at the cosmic origin point. The singularity theorems essentially tell you that the early universe was once so incredibly small that the effects described by the other great pillar of 20th century physics, quantum mechanics, must have been dominant. Therefore, by the early 1970s, our quest to understand the universe had to pivot from the realm of the immensely large to that of the infinitesimally small. In the early 19th century, the French scientist Pierre Laplace, deeply impressed by the triumphs of scientific theories like Newton's law of gravitation, conceived of the cosmos as an entirely deterministic machine. He was convinced that a complete set of scientific laws must exist, which, given a perfect snapshot of the universe at one instant, would enable us to foresee every future event. While this determinism seems straightforward when calculating planetary orbits using Newton's laws, Laplace controversially extended the idea to encompass everything, including human behavior, a doctrine that met with considerable resistance from those who saw it as a challenge to divine agency. Despite this opposition, the concept of scientific determinism became a standard assumption in science for the next century. However, some of the first evidence that this idea might be flawed emerged from the calculations of two English physicists, John Rayleigh and James Jeans. Their work indicated that a hot body, like a star, should theoretically radiate an infinite quantity of energy, because existing laws suggested it would emit electromagnetic waves of all frequencies equally. This implied that the total radiated energy, summed across an infinite number of frequencies, would itself be infinite, a conclusion that was clearly absurd. To resolve this paradox, German scientist Max Planck introduced a revolutionary idea in 1900. He proposed that light, X-rays, and other waves are not emitted continuously, but in discrete packets he named quanta. Planck further theorized that the energy of each quantum is directly proportional to its wave frequency. Consequently, at very high frequencies, the energy required for even a single quantum would surpass the total energy available, effectively suppressing such radiation. This quantum hypothesis not only explained the observed energy output from hot bodies perfectly, but also laid the groundwork for a new understanding of physics. The full consequences of Planck's work for determinism only became apparent in 1926, when another German scientist, Werner Heisenberg, formulated his celebrated uncertainty principle. To predict a particle's future, you would need to measure its current position and velocity with absolute precision. The problem, as Heisenberg realized, is that the very act of observation interferes with the particle. To pinpoint a particle's location, you must shine light on it, and some of that light will scatter, revealing its position to you. The accuracy of such a measurement is limited by the wavelength of the light used. To get a precise position, you need light with a very short wavelength. However, according to Planck's discovery, light can only be used in minimum amounts of one quantum. A quantum of short wavelength high-frequency light carries a great deal of energy, and its impact will inevitably disturb the particle, altering its velocity in an unpredictable way. Essentially, the more precisely you attempt to measure a particle's position, the less accurately you can possibly know its velocity. And the reverse is also true. Heisenberg demonstrated that the uncertainty in a particle's position, when multiplied by the uncertainty in its velocity and its mass, can never fall below a specific value, which we now call Planck's constant. This is not a limitation of our instruments, but a fundamental and inescapable property of the world itself. The uncertainty principle has profound implications for our view of reality, and even after more than half a century, its full meaning remains a subject of intense debate among many philosophers. This principle effectively marked the end of Laplace's vision of a completely deterministic scientific model of the universe. After all, if we cannot measure the present state of the cosmos with perfect accuracy, how could we ever hope to predict its future with certainty? While one could speculate about a supernatural being capable of observing the universe without disturbing it, such models hold little practical value for us. It is more rational to apply the principle of economy known as Occam's razor and eliminate all theoretical components that cannot be observed. Following this logic, Werner Heisenberg, along with Erwin Schrödinger and Paul Dirac, reformulated physics into a new theory known as quantum mechanics. Within this framework, particles are no longer conceived as having separate, well-defined positions and velocities that are simply hidden from us. Instead, their state is described by a quantum state, which is an integrated combination of both position and velocity. Quantum mechanics fundamentally alters the nature of scientific prediction. It does not provide a single, definite outcome for an observation. Instead, it offers a range of different possible results and calculates the probability for each one to occur. This means that quantum mechanics introduces an unavoidable element of unpredictability and randomness into the very heart of science, forever changing our perception of the cosmos. Despite his own pivotal role in its creation, Albert Einstein vehemently opposed the central premise of quantum theory. Although he was honored with the Nobel Prize for his immense contributions to the field, he could never accept that the cosmos operates on principles of pure chance. His conviction was famously articulated in his statement, "God does not play dice." Yet the majority of scientists embraced quantum mechanics because its predictions flawlessly matched experimental results. Indeed, quantum mechanics has proven to be an extraordinarily successful theory, providing the fundamental principles for nearly all of modern science and technology. Its laws dictate the behavior of essential electronic components like transistors and integrated circuits, which are the heart of devices such as televisions and computers. Furthermore, quantum mechanics serves as the very foundation for contemporary chemistry and biology, with its reach yet to fully encompass only the domains of gravity and the large-scale structure of the universe. While light is composed of waves, Max Planck's quantum hypothesis revealed that it also behaves as if it were made of particles, which are emitted and absorbed only in discrete packets known as quanta. Conversely, Werner Heisenberg's uncertainty principle suggests that particles act like waves in some respects. They lack a precise location and are instead smeared out across a distribution of probabilities. This led quantum mechanics to adopt a completely new mathematical framework, one that no longer describes an objective reality of particles and waves, but treats these as concepts applicable only to the results of measurement. This framework introduces the concept of wave-particle duality, where it is sometimes useful to think of particles as waves, and, in other scenarios, to treat waves as particles. A significant outcome of this duality is the ability to observe interference between two waves, or even two particles. For instance, the crest of one wave can align with the trough of another, leading them to cancel each other out, or they can align to reinforce one another, producing a much stronger combined wave. A classic illustration of light interference is the rainbow of colors you see, shimmering on the surface of soap bubbles. This effect is produced by light reflecting off both the inner and outer surfaces of the thin water film. Since white light is a composite of all colors, or wavelengths, the crests of some waves bouncing off one surface will meet the troughs of waves of the same color from the other surface. This cancellation removes specific colors from the reflected light, which is why it appears multicolored. Because of the wave-particle duality inherent in quantum mechanics, particles themselves can also demonstrate interference. The double-slit experiment is a renowned demonstration of this principle. Imagine a barrier containing two narrow parallel slits, with a light source of a single color, meaning a single wavelength, on one side. While most of the light is blocked, a small amount passes through the slits. An observation screen placed on the other side reveals that the light waves from both slits interfere, creating a characteristic pattern of light and dark bands. What is truly remarkable is that if you substitute the light source with a source of particles like electrons, emitted at a specific velocity, you get exactly the same pattern of interference bands. Even more puzzling is what happens if you close one of the slits. The bands disappear, and you simply see a uniform distribution of electrons. One might logically assume that adding a second slit would just increase the number of electrons hitting the screen. But due to interference, it actually reduces the count in certain areas. The phenomenon becomes even more profound when particles are sent toward the slits one at a time. In this scenario, each individual particle must somehow pass through both slits at once and interfere with itself. If each electron passed through only one slit or the other, as if it were the only one open, the result would be a simple, uniform distribution. Instead, even when sent one by one, the electrons gradually build up the same interference pattern, confirming that each particle navigates both paths simultaneously. This property of particle interference became absolutely critical for developing our understanding of atomic structure, the basis of all chemistry, biology, and the matter that makes up you and everything around you. In the early 20th century, the prevailing model depicted atoms as miniature solar systems, where negatively charged electrons were thought to orbit a central, positively charged nucleus, much like planets orbit the sun. The electrical attraction between the opposite charges was presumed to hold the electrons in their orbits, mirroring the role of gravity in our solar system. The issue with this model was that, according to the laws of mechanics and electricity before quantum theory, electrons should continuously lose energy. This energy loss would cause them to spiral inward until they collapsed into the nucleus, suggesting that all atoms, and therefore all matter, should rapidly contract into a state of incredible density. A partial solution to this paradox was proposed in 1913 by the Danish scientist Niels Bohr, who theorized that electrons could only occupy certain specific orbits at fixed distances from the nucleus. If you assumed that any such orbit could contain only one or two electrons, the issue of atomic collapse would be resolved, since electrons spiraling inward would be forced to occupy the orbits with the lowest possible radii and energies. This model provided a flawless explanation for the structure of the most basic atom, hydrogen, which possesses just a single electron circling its nucleus. The challenge, however, was in figuring out how this same approach could be applied to more intricate atoms, and the premise of a fixed number of permissible orbits seemed entirely arbitrary. The solution to this predicament emerged from the new theory of quantum mechanics. As it turned out, you can visualize an electron orbiting a nucleus as a wave whose wavelength is determined by its velocity. Along certain specific orbits, an exact whole number of electron wavelengths can fit perfectly, causing the wave crests to align with each other revolution and mutually reinforce one another. These particular paths correspond directly to Bohr's allowed orbits, whereas for all other trajectories, the waves would destructively interfere and cancel each other out, making those orbits impossible. The American physicist Richard Feynman developed a remarkably elegant way to picture this wave-particle duality. He introduced a concept known as the path integral formulation, which, in a departure from classical theory, does not presume a particle follows a single definite trajectory through spacetime. Instead, Feynman's model posits that a particle travels from a point A to a point B by taking every conceivable path simultaneously. Each of these paths is defined by two numbers. One represents the wave's amplitude, or size, and the other specifies its phase, or position in the cycle, such as a crest or a trough. To calculate the probability of a particle moving from point A to point B, you must sum the waves associated with all these different paths. For most adjacent paths, their phases will vary so widely that their corresponding waves effectively cancel each other out. Yet, for particular sets of paths where the phase changes minimally from one to the next, the waves do not cancel, and instead reinforce one another. It is precisely these reinforced paths that align with Bohr's allowed orbits. Using these principles, expressed through a specific mathematical framework, it became possible to compute the allowed orbits for more complex atoms and even molecules, which consist of multiple atoms bound together by electrons orbiting more than one nucleus. Because the structure of molecules and their interactions are the foundation of all chemistry and biology, quantum mechanics can, in theory, predict everything we observe around us, within the limits imposed by the uncertainty principle. In practice, however, the calculations required for systems with numerous electrons become so overwhelmingly complex that they are impossible to carry out. The large-scale fabric of the universe seems to be dictated by Einstein's general theory of relativity. This is considered a classical theory because it doesn't incorporate the quantum mechanical uncertainty principle, which is essential for it to harmonize with other physical theories. We don't notice contradictions with observations because the gravitational fields we normally encounter are extremely weak. However, the singularity theorems I mentioned earlier predict that gravitational fields must become immensely powerful in at least two scenarios: inside black holes and at the Big Bang. In the presence of such intense fields, quantum effects are expected to become critically important. Consequently, by predicting points of infinite density, classical general relativity effectively foretells its own limitations, much like classical mechanics doomed itself by concluding that atoms should collapse to an infinite density. We still do not possess a complete and consistent theory that successfully merges general relativity with quantum mechanics, but we have identified certain properties such a future theory must possess, and we will explore their implications for black holes and the Big Bang in subsequent chapters. For now, Let's turn our attention to the more recent efforts to combine our knowledge of all the other forces of nature into a unified quantum theory. Aristotle proposed that all matter in the cosmos consisted of 4 basic elements: earth, air, fire, and water. He believed these elements were influenced by 2 fundamental forces: gravity, which drew earth and water downward, and levity, which compelled fire and air to ascend. This fundamental division of the universe into matter and forces continues to shape our thinking even today. According to Aristotle's philosophy, matter was continuous, meaning you could take any piece of it and divide it into progressively smaller fragments indefinitely, without ever reaching a fundamental, indivisible particle. In contrast, other Greek thinkers like Democritus argued that matter was inherently granular, composed of a vast number of distinct atoms, a term derived from the Greek word for indivisible. This debate persisted for centuries, with neither side having any conclusive evidence to support its claims. It was not until 1803 that the English chemist and physicist John Dalton made a breakthrough, demonstrating that the consistent proportions in which chemical substances combine could be explained if atoms merge to create units known as molecules. Even so, the dispute between the 2 philosophical schools wasn't settled in favor of the atomists until the dawn of our own century. A pivotal contribution came from Albert Einstein in a paper he wrote in 1905, just weeks before his seminal work on special relativity. Einstein showed that the phenomenon called Brownian motion, the erratic, haphazard movement of tiny specks suspended in a liquid, could be perfectly explained as the result of these particles being bombarded by the liquid's own atoms. By that point in time, there were already mounting suspicions that atoms themselves might not be indivisible after all. Several years prior, J.J. Thomson at Cambridge had discovered a new constituent of matter, the electron, a particle with a mass less than 1/1000th that of the lightest atom. J.J. Thomson's experimental device was somewhat like a modern cathode ray television tube, using a red-hot metal filament to generate electrons. Because electrons carry a negative charge, an electric field could accelerate them toward a screen that was coated with a phosphor, causing flashes of light wherever they struck. It quickly became apparent that these electrons had to be originating from within atoms themselves. Then, in 1911, the English physicist Ernest Rutherford definitively proved that atoms possess an internal structure, consisting of a minuscule, positively charged nucleus, with electrons orbiting it. Rutherford formulated this conclusion by observing how alpha particles, which are positively charged particles emitted by radioactive elements, were deflected during collisions with atoms. At first, the scientific community presumed that the atomic nucleus was composed of electrons and positively charged particles called protons, a name derived from the Greek word protos, meaning primary, as they were seen as matter's essential building blocks. This understanding changed in 1932 when James Chadwick, one of Rutherford's colleagues at Cambridge University, discovered that the nucleus also housed neutrons, which had a mass nearly identical to protons but possessed no charge. Chadwick's discovery earned him the Nobel Prize, and later, the position of Master of Gonville and Caius College, Cambridge, though he eventually had to resign from the post due to conflicts with his colleagues over academic appointments. For about 20 years, both protons and neutrons were regarded as elementary particles. However, experiments that involved colliding high-speed protons and electrons with other protons demonstrated that these particles were themselves constructed from even smaller components. Murray Gell-Mann, a theorist at the California Institute of Technology, gave these tiny constituents the name quarks. For his theoretical work on quarks, Gell-Mann was awarded the Nobel Prize in 1969. The name itself was inspired by a whimsical line from James Joyce, "3 quarks for Muster Mark." While the word was meant to be pronounced like quart, it is more commonly made to rhyme with lark. There are several varieties of quarks, and it's thought that at least 6 flavors exist: the up, down, strange, charm, bottom, and top quarks. Furthermore, each flavor of quark can manifest in one of 3 colors: red, green, or blue. It is important for you to understand that these terms are simply descriptive labels. Quarks are much smaller than the wavelength of visible light, so they do not possess color in the ordinary sense. Modern physicists simply have a penchant for creating inventive names for new particles and phenomena, no longer confining themselves to the Greek alphabet. A proton is composed of 2 up quarks and 1 down quark, while a neutron is made of 2 down quarks and 1 up quark, with each triplet containing 3 different colors. While particles can be assembled from the other quarks, strange, charm, bottom, and top, these are all far more massive and rapidly decay into the more stable protons and neutrons. We are now aware that neither atoms nor the protons and neutrons inside them are indivisible. This prompts the question: what is the truly elementary particle, the ultimate building block of everything? Because the wavelengths of light are far too long compared to the size of an atom, you cannot hope to see an atom's components through conventional means. To probe such small scales, we require something with a much shorter wavelength. According to quantum mechanics, all particles also behave as waves, and the greater a particle's energy, the shorter its corresponding wavelength is. Thus, the answer to our question hinges on the maximum energy we can impart to particles, which in turn determines the finest scale of reality we can observe. The energy of particles is typically measured in a unit called the electron volt. In Thomson's experiments, electrons were accelerated by an electric field, and 1 electron volt represents the energy an electron acquires in a field of 1 volt. During the 19th century, when the only accessible particle energies were a few electron volts from chemical reactions like burning, atoms were logically considered the smallest unit of matter. Rutherford's work involved alpha particles with energies in the millions of electron volts. Since then, we have developed methods to use electromagnetic fields to accelerate particles first to millions and eventually to billions of electron volts. This advancement revealed that the particles considered fundamental just 2 decades ago are actually composites of even smaller entities. It is certainly plausible that by reaching even higher energies, we might find that these particles are also made of something smaller still. However, we currently possess theoretical grounds to believe that we are either at or very near to identifying the true, fundamental constituents of nature. Every single thing that exists in the universe, including phenomena like light and gravity, can be described in terms of particles when you take wave-particle duality into account. You can try to picture these particles as tiny spinning tops, each rotating on its own axis. This image, however, can be misleading, as quantum mechanics tells us that particles do not have a clearly defined axis of rotation. In reality, a particle's spin is a property that describes how it appears when viewed from different directions. A particle with a spin of 0 is like a simple point. It appears identical from every angle. A particle with a spin of 1 is comparable to an arrow. It looks different depending on the direction you view it from, and only seems the same after a complete 360-degree rotation. A spin 2 particle is like a double-headed arrow, looking unchanged after just a half turn of 180 degrees. By extension, Particles with higher spins return to their original appearance after rotating by even smaller fractions of a full circle. It's a fascinating fact that some particles require 2 complete rotations, not just one, to restore their original orientation. These are known as particles with spin 1/2. Every known particle in the cosmos falls into one of 2 categories. The spin 1/2 particles constitute all the matter you see, while particles with spin 0, 1, and 2 generate the forces that act between them. The particles that make up matter all follow a rule known as the Pauli exclusion principle, which was discovered in 1925 by the Austrian physicist Wolfgang Pauli. For this breakthrough, Pauli was awarded the Nobel Prize in 1945. He was the quintessential theoretical physicist, so much so that it was joked his mere presence in a city was enough to disrupt any experiment. The principle itself states that 2 identical particles cannot occupy the exact same state, meaning they cannot share the same position and velocity within the limits defined by the uncertainty principle. The significance of the Pauli exclusion principle is immense, as it explains why particles of matter, under the influence of forces from particles with spin 0, 1, or 2, do not collapse into a state of extreme density. If this principle didn't exist, all particles would compress together and matter would form a nearly uniform dense soup. A proper understanding of the electron and similar spin 1/2 particles was missing until 1928, when Paul Dirac put forward a theory to describe them. Dirac, who later held the Lucasian Professorship of Mathematics at Cambridge, a position once held by Newton, developed the first theory to be consistent with both quantum mechanics and special relativity. It mathematically explained why an electron has spin 1/2, clarifying why it must rotate twice, not once, to return to its original state. Furthermore, Dirac's theory predicted that the electron must have a partner, an anti-electron, or positron. The discovery of the positron in 1932 provided confirmation of Dirac's theory, earning him the Nobel Prize in Physics in 1933. We are now aware that for every particle, there is a corresponding antiparticle with which it can annihilate. For force-carrying particles, it's often the case that the particle and its antiparticle are one and the same. Entire anti-worlds, and even anti-people, made from antiparticles, could theoretically exist. However, if you ever happen to meet your anti-self, I would strongly advise against shaking hands. The contact would result in a blinding flash of light as you both vanish. This leads to a profoundly important question. Why do we observe so many more particles than antiparticles around us? In quantum mechanics, it is understood that all forces or interactions between matter particles are carried by particles with an integer spin of 0, 1, or 2. A matter particle, such as an electron or a quark, emits one of these force-carrying particles, and the recoil alters its velocity. This force carrier then travels to and is absorbed by another particle of matter. This absorption changes the second particle's velocity, creating the effect you would perceive as a force acting between the two. These force-carrying particles have a vital property. They do not obey the Pauli exclusion principle. This lack of restriction means there is no limit to how many particles can be exchanged, which allows the forces they generate to be incredibly strong. However, if these force-carrying particles have a large mass, creating and exchanging them over long distances becomes difficult, resulting in short-range forces. Conversely, if the force carriers are massless, they give rise to long-range forces. The particles that mediate these forces are called virtual because, unlike real particles, a detector cannot observe them directly. We know these virtual particles exist because of the measurable effects they produce. It is through them that forces arise between particles of matter. Under certain conditions, particles with spin 0, 1, or 2 can manifest as real particles, which can then be directly detected. From the viewpoint of classical physics, these real particles appear to you as waves, such as light waves or gravitational waves. For example, the repulsive electrical force between two electrons is caused by the exchange of virtual photons, which are undetectable. But if these electrons pass near each other, they can emit real photons, which you can detect as light waves. Force-carrying particles can be sorted into 4 types, categorized by the strength of the force they carry and the particles they interact with. It is important to emphasize that this division is a human construct, created as a convenient way to develop partial theories. The ultimate hope for most physicists is to create a unified theory where all 4 forces are shown to be different aspects of a single, fundamental force. Indeed, many would consider this the main goal of modern physics. Recently, significant progress has been made in unifying 3 of the 4 forces, and I will get to how gravity might fit into this picture a little later. The first of these forces is the gravitational force. Gravity is universal, meaning that every particle in the universe is subject to its influence, with a magnitude determined by its mass or energy. It is far weaker than the other 3 forces, so weak, in fact, that you wouldn't notice it at all if not for 2 key properties. Gravity acts over vast distances, and it is always attractive. You can see, then, how the incredibly faint gravitational pull between individual particles can accumulate across 2 massive objects, like the Earth and the Sun, to create an immensely powerful force. In the quantum mechanical view, a particle with a spin of 2, known as the graviton, is responsible for carrying the gravitational force between 2 particles of matter. Because the graviton possesses no intrinsic mass, the force it mediates has a very long range. The gravitational dance between the Sun and the Earth is accounted for by the constant exchange of these gravitons between the particles composing each celestial body. Even though the exchange involves only virtual particles, the outcome they produce is undeniably real and measurable. It's what keeps the Earth in its orbit around the Sun. If gravitons were to propagate as real particles, they would manifest as what classical physics calls gravitational waves. These waves are so exceptionally weak, however, that their detection has proven to be an extraordinary challenge. The next fundamental interaction is generated by electromagnetic forces, which influence electrically charged particles like electrons and quarks, but have no effect on neutral particles such as gravitons. Electromagnetic interactions are vastly more powerful than their gravitational counterparts. In fact, the electromagnetic repulsion between 2 electrons is stronger than their gravitational attraction by a factor of roughly 10 to the 42nd power. However, electric charge comes in 2 varieties, positive and negative. While like charges repel one another, opposite charges attract. In large-scale bodies like the Earth or the Sun, the numbers of positive and negative charges are so finely balanced that the attractive and repulsive forces almost perfectly negate each other, resulting in a negligible net electromagnetic force. At the microscopic level of atoms and molecules, however, electromagnetic forces are completely dominant. It is the electromagnetic attraction between negatively charged electrons and the positively charged protons within the nucleus that compels electrons to orbit that nucleus, in a manner analogous to how gravity dictates the Earth's path around the Sun. This attraction is understood as the result of exchanging a vast number of massless, virtual particles with a spin of 1, which we call photons. Just as with gravitons, these exchanged photons are virtual. Yet, when an electron transitions from one permitted orbit to another one closer to the nucleus, a release of energy occurs, and a real photon is emitted. This emitted photon, if it possesses the correct wavelength, can be perceived by the human eye as visible light, or captured by a device like photographic film. Conversely, if a real photon strikes an atom, it can cause an electron to jump to an orbit farther from the nucleus, a process in which the photon's energy is completely absorbed. The third type of fundamental interaction is the weak nuclear force, which is the mechanism behind radioactivity, and which affects all matter particles with a spin of 1/2. You should note, however, that particles with spins of 0, 1, or 2, such as photons and gravitons, are immune to this interaction. Our comprehension of the weak force remained quite poor until 1967, the year Abdus Salam from Imperial College London and Steven Weinberg from Harvard independently put forward a theory that unified the weak interaction with electromagnetism, in a way that mirrored how Maxwell had united electricity and magnetism a century before. Weinberg and Salam proposed that 3 other spin 1 particles, which they collectively named heavy vector bosons, existed alongside the photon to carry the weak force. These particles were designated W+, W-, and Z0, and each was predicted to have a mass equivalent to about 100 giga-electronvolts. The Weinberg-Salam theory includes a feature called spontaneous symmetry breaking, which suggests that particles appearing radically different at low energies are, in reality, the same entity in different states at very high energies. To help you picture this, consider the motion of a ball on a roulette wheel. At high energies, when the wheel spins fast, the ball's behavior is essentially uniform. As the wheel decelerates and the ball's energy drops, it inevitably settles into one of the 37 available slots. In this way, the ball can exist in 37 distinct states at low energies. If you could only observe the ball in these low-energy conditions, you might incorrectly conclude that 37 different kinds of balls exist. The Weinberg-Salam theory made the prediction that at energy levels far exceeding 100 giga-electronvolts, the 3 new bosons and the photon would all behave identically. At lower energies, this symmetry would break, causing the W+, W-, and Z0 particles to gain significant mass, and thereby making the forces they mediate extremely short-ranged. When the theory was first proposed, very few people took it seriously, and the particle accelerators of that era couldn't generate the 100 GeV needed to create real W and Z particles. Nevertheless, over the subsequent decade, the theory's low-energy predictions were so successfully confirmed by experiments that Weinberg, Salam, and Sheldon Glashow, who had developed a similar unified model, were awarded the 1979 Nobel Prize. The Nobel Committee was saved any potential embarrassment when, in 1983, the 3 massive counterparts to the photon were finally discovered at CERN, possessing the predicted mass and other properties. This achievement earned Carlo Rubbia, the leader of the discovery team, and Simon Vandermeer, the CERN engineer behind the essential antiparticle storage system, the 1984 Nobel Prize. Finally, the fourth fundamental interaction is the strong nuclear force. This is the force that confines quarks within protons and neutrons, and it is also what binds those protons and neutrons together to form the nuclei of atoms. It has become nearly impossible for me to conceive of experimental physics without these landmark accomplishments. Unless, of course, you have already reached the very zenith of the field. The strong interaction is mediated by a particle known as the gluon, which has a spin of 1. These gluons exclusively engage with quarks and with each other, and a remarkable characteristic of the strong interaction is a principle called confinement. This means that particles subject to this force are always bound together in combinations that are colorless. You can never find an isolated quark, as it would possess a distinct color charge of red, green, or blue. To achieve this required color neutrality, a red quark, for example, is bound by gluon strings to a green and a blue quark, forming a colorless triplet that can constitute a proton or a neutron. Alternatively, a quark can pair with an antiquark of a corresponding anticolor, such as red and anti-red, to create a meson, which is also a colorless particle. The rule of confinement applies to gluons as well, since they also carry a color charge, preventing them from existing in isolation. Instead, gluons are forced to cluster together into groups whose colors cancel out to form a neutral state. This grouping of gluons creates a highly unstable particle referred to as a glue ball. However, you shouldn't think that this confinement makes the idea of individual quarks and gluons purely abstract. The strong interaction possesses another key feature known as asymptotic freedom, which helps solidify the particle status of quarks and gluons. Under normal energy conditions, the strong force is incredibly powerful, binding quarks together very tightly. Yet, as demonstrated by experiments using high-capacity accelerators, this force diminishes dramatically at very high energies, allowing quarks and gluons to act almost as if they were independent, free particles. Following the successful merging of the electromagnetic and weak forces, physicists embarked on efforts to integrate the strong interaction as well, leading to the development of what we call a grand unified theory, or GUT. I find this label to be a bit of an overstatement, as these theories are not quite as grand as they sound. They fall short of a complete unification because they fail to incorporate gravity, and they are also incomplete frameworks containing certain parameters that theory cannot predict. The foundational concept of a GUT builds on the fact that the strong force weakens at high energies, while the electromagnetic and weak forces actually intensify. The theory suggests that at an immense energy level, known as the grand unification energy, these three forces would converge to the same strength. At this threshold, GUTs also forecast that distinct matter particles with a spin of 1/2, like quarks and electrons, would become fundamentally indistinguishable. The predicted grand unification energy is estimated to be approximately 1 trillion giga-electron volts. To put that into perspective for you, contemporary particle accelerators can achieve collision energies of about 100 giga-electron volts. Reaching the grand unification energy, however, would necessitate an accelerator on the scale of our solar system, a project so vast that its funding seems inconceivable in today's economic environment. Consequently, it's impossible for us to directly test a grand unified theory through experiment. Much like the electroweak theory, however, we can look for low-energy effects that these theories predict. The most captivating of these predictions is the possibility that protons, which account for a significant portion of the mass of all ordinary matter you see, could spontaneously break down into lighter particles like anti-electrons. The underlying logic for this decay is that at the grand unification energy, there is no fundamental distinction between a quark and an anti-electron. While the three quarks constituting a proton typically lack the energy to make this conversion, the uncertainty principle means a single quark could, by pure chance, momentarily acquire enough energy to trigger the proton's decay. The likelihood of a quark gaining this much energy is so incredibly small that you would need to wait a minimum of 10 to the 30th power years to witness such an event. This duration is profoundly longer than the entire history of the universe since the Big Bang, which is less than 10 to the 10th power years. This enormous timescale would seem to make the experimental verification of spontaneous proton decay impossible. Yet, you can enhance the chances of detecting a proton decay by monitoring an immense number of them simultaneously. For instance, according to some of the more straightforward grand unified theories, if you were to observe a quantity of protons on the order of 10 to the 31st power for just 1 year, you might expect to witness more than a single decay event. A number of these large-scale experiments have been carried out, yet none have produced conclusive proof of either proton or neutron decay. One notable effort involved using 8,000 tons of water situated deep within an Ohio salt mine to shield it from cosmic rays that might mimic a decay signal. Based on this experiment's outcome of 0 recorded decays, we can infer that a proton's lifetime must exceed 10 to the 31st power years. This finding surpasses the predictions of the simplest GUT, but it doesn't rule out more sophisticated versions of the theory. To truly validate these theories, we will need experiments of even greater precision that involve significantly larger quantities of matter. Yet, despite the challenge of detecting proton decay, it's conceivable that your very existence hinges on the opposite process: the creation of protons, or, more fundamentally, quarks, during the universe's infancy, when quarks and antiquarks were in equal measure. This particular view of how everything began appears to be the most logical one. The matter on Earth, and indeed everything you can see, is predominantly built from protons and neutrons, which themselves are composed of quarks. It is conspicuously devoid of antiprotons and antineutrons, their antiquark-based counterparts, save for a handful created fleetingly in powerful accelerators. Observations of cosmic rays further reinforce that this is true for our entire galaxy. Apart from the small fraction of antiparticles generated in high-energy collisions, antiprotons and antineutrons are simply not present. Should our galaxy contain vast domains of antimatter, we would detect intense radiation flaring at the boundaries where matter and antimatter meet, leading to mass annihilation events. While we lack direct proof about the composition of other galaxies, we know that any single galaxy must be made of one type of substance. A mixture of particles and antiparticles is impossible, as their constant annihilation would produce an unmistakable and powerful radiative signature that we do not observe. Consequently, the prevailing belief is that all galaxies are constructed from quarks rather than antiquarks, making it improbable that the cosmos is a patchwork of matter and antimatter galaxies. This raises a critical question. Why does this profound surplus of quarks exist? It is incredibly fortunate for you that it does, because if their numbers had been equal, nearly all quarks and antiquarks would have annihilated in the primeval universe, leaving behind a cosmos filled with radiation, but almost no matter at all. Without this imbalance, there would be no galaxies, no stars, and certainly no planets upon which human life could emerge. The solution may lie in grand unified theories, which propose a mechanism for how more quarks than antiquarks could exist today, even if their populations were initially balanced. As I've discussed, These theories suggest that at incredibly high energies, quarks can convert into particles like anti-electrons, and the reverse processes are also possible. In the tremendously hot, early stages of the universe, the energy of particles was more than sufficient to fuel these transformations. The reason more quarks survived is that the fundamental laws of physics do not apply identically to particles and antiparticles. For a long time, it was assumed that physical laws were unchanging under three key symmetries: C, P, and T. C symmetry implies that the laws are identical for particles and antiparticles. P symmetry, or parity, means that the laws of physics remain the same for any event and its mirror reflection. For example, a particle spinning clockwise would appear as a particle spinning counterclockwise in a mirror. Lastly, T symmetry suggests that if you were to reverse the motion of every particle, the system would revert to a previous state, meaning the laws work the same forwards or backwards in time. However, in 1956, American physicists Tsung-Dao Lee and Chen-Ning Yang proposed that the weak nuclear force is not actually symmetric under P transformations, meaning the universe might not behave identically to its mirror image. That same year, their colleague Chien-Shiung Wu experimentally proved their hypothesis correct, for which Lee and Yang received the Nobel Prize. It was soon discovered that the weak interaction also violates C symmetry, implying an antimatter universe would operate differently from our own. It was still thought, however, that the laws must obey a combined CP symmetry, where an event would look the same as its mirror image if all particles were also swapped for their antiparticles. But in 1964, two more Americans, James Cronin and Val Fitch, showed that even this combined CP symmetry is broken during the decay of particles known as kaons. This discovery, which earned them the Nobel Prize in 1980, was another testament to the universe's underlying complexity. A core mathematical theorem asserts that any theory consistent with quantum mechanics and relativity must respect the combined CPT symmetry. In other words, the universe's behavior should be unchanged if you swap all particles for antiparticles, create a mirror image, and reverse the direction of time. Since Cronin and Fitch proved that the CP part of this symmetry is violated, it logically follows that the laws of physics must also change when time is reversed. They cannot be T-symmetrical. In the early universe, as time moved forward and space expanded, this violation of time symmetry was crucial. Because forces exist that are not invariant under T-symmetry, the expansion of the cosmos favored certain reactions over others. These forces caused anti-electrons to transform into quarks more frequently than electrons transformed into antiquarks. As the universe then expanded and cooled, the vast majority of quarks and antiquarks annihilated each other. But the slight initial surplus of quarks remained, forming the foundation of everything that exists today. Because there were more quarks than antiquarks, a slight surplus of quarks would survive, and these are the very particles that constitute all the matter you see around you, including our own bodies. In this sense, our existence itself offers a form of qualitative proof for grand unified theories. The confirmation remains uncertain, however, as we are unable to calculate the precise number of quarks that would survive the annihilation, or even definitively know if the remainder would be quarks or antiquarks. Had antiquarks prevailed, you see, we would have simply reversed the names, calling them quarks instead. Grand unified theories do not account for the interaction of gravity. This omission is generally not a major issue, as gravitational forces are so faint that their effects can be disregarded when analyzing elementary particles and atoms. Nevertheless, gravity is a long-range force that is exclusively attractive, which means its influence is cumulative. For this reason, with a sufficient accumulation of matter, gravitational forces can overwhelm all other interactions, which is precisely why gravity governs the evolution of the cosmos. Even on the scale of stars, gravitational pull can overpower all competing forces, compelling the star to undergo a catastrophic collapse. My own work has involved an intensive study of black holes, which can be born from such stellar events, and the powerful gravitational fields that envelop them. It was through this research that I first started to perceive how quantum mechanics and general relativity might intertwine, catching the initial hints of a quantum theory of gravity that has yet to be fully formulated.